8.3 Situations involving kinetic friction. The outline of this video is as follows. We will discuss modeling kinetic friction and its relationship to work. Then, we will derive the modified work-energy relation that accounts for friction. We will also define the change in internal energy, which is represented as delta E sub int. Finally, we will apply these concepts to two detailed examples: a block pulled on a rough surface, and a block spring system that includes friction. We must first understand why kinetic friction complicates our energy calculations. The central issue is that the work done by the friction force is not calculable. This is because the displacement of the object is not the same as the displacement of the point of application of the friction force. For example, in a simplified model, the object might move a distance d, but the tiny irregularities causing friction might only move a distance d over 2. In a real scenario, the force is spread over a complex area, making the displacement of its application point impossible to calculate. Because we cannot find the work done by friction, the standard work-kinetic energy theorem is not valid in this case. The key takeaway is that we need a different approach, even though Newton's second law remains valid. Since we cannot use the standard theorem, we will derive a modified relation. We begin by considering the work done by all forces other than friction, which we write as the sum of W other forces. This is equal to the integral of the sum of F other forces dr. Next, we add a specific term to both sides of the equation, the integral of the friction force vector, F sub k dot dr. It is important to note this is not defined as work. After adding this term, the integrand on the right side now contains the sum of all forces, which is the net force. Using Newton's second law, we can replace this net force with mass times acceleration, or m times a. Our modified relation now shows that W other forces plus the friction integral equals the integral of ma dot dr. Let us continue by evaluating the right side of our equation, which is the integral of ma dot dr. We can substitute acceleration, a, with d, versus over dt, and the displacement, dr, with v times dt. This changes the integral to the integral of m times the quantity d, versus over dt dot v, all times dt. We then use a helpful calculus identity. The expression d versus over dt dot v is equal to 1/2 times the derivative of v squared with respect to t. Substituting this in and integrating, we find the right side simplifies to 1/2 m's versus final squared minus 1/2 m's versus initial squared. This is, by definition, the change in kinetic energy, delta K. Our final derived relation is that the sum of work done by other forces plus the integral of F sub k dot dr equals delta K. We can now finalize our modified relation. For an object that is sliding, the kinetic friction force vector, F sub k, and the displacement vector, dr, are always in opposite directions. Because they are 180 degrees apart, their dot product, F sub k dot dr, simplifies to the negative product of their magnitudes, which is negative F sub k dr. Substituting this into our equation gives us the sum of work by other forces minus the integral of F sub k dr equals delta K. This is a very useful result. If we also assume that the friction force F sub k is constant over the motion, we can pull it out of the integral. The integral of dr is just the total path length, which we can call d. Our final equation is W minus F sub k times d equals delta K, where W is the work done by all forces except friction. Let us now connect this to the concept of internal energy. Consider an isolated system, like a book sliding to a stop on a surface, where no external forces do work, so W equals 0. Our derived relation, W minus F sub kd equals delta K, simplifies to delta K equals negative F sub kd. The energy principle for this system states that the change in kinetic energy plus the change in internal energy must be 0. By substituting our new expression for delta K, we get negative F sub kd plus delta E sub int equals 0. This provides a powerful conclusion. The change in internal energy due to friction, delta E sub int, is equal to the friction force, F sub k times the path length d. Friction transforms kinetic energy into internal energy. For a non-isolated system, where other forces do work, our full energy model becomes W equals delta K plus delta E sub int. Here's a quick quiz to check your understanding. You are traveling along a freeway at 65 miles per hour, so your car has a significant amount of kinetic energy. You suddenly skid to a stop due to a traffic jam. The question is, where is the kinetic energy your car once had? The correct answer is C. The friction between the skidding tires and the road transforms a large amount of the kinetic energy into internal energy, which you would feel as heat in both the tires and the road surface. Additionally, the process of skidding creates loud sounds and vibrations. These are mechanical waves, which also carry energy away from the car road system. Let us now apply our energy model to example 8.5. In part A, we have a 6.0 kilogram block, which is initially at rest. It is pulled to the right by a constant horizontal force of 12 newtons and moves 3.0 meters. The coefficient of kinetic friction, mu sub k, is 0.15. Our goal is to find the final speed. We will model this as a non-isolated system that includes a non-conservative force, which is friction. The energy equation we will use is the change in kinetic energy, delta K, plus the change in internal energy, delta E sub int, equals the work done by the external force, W. In this case, W is the work done by the applied 12 Newton force, so W equals F times D. The change in internal energy is given by F sub K times D. We find the friction force, F sub K, by noting that the normal force, N, balances gravity, mg. Therefore, F sub K equals mu sub k times mg. Now we substitute all our terms into the energy equation, delta K plus delta E sub int equals W. The change in kinetic energy is 1/2 m versus final squared minus 0. The change in internal energy is mu sub k times mg times d. The work done by the applied force is F times d. This gives us the full equation, 1/2 m versus final squared plus mu sub kmgd equals fd. We can now solve this expression for the final velocity, v sub f. Algebraically, v sub f equals the square root of the quantity 2 times d multiplied by the quantity f over m minus mu sub kg. Plugging in our numerical values, we get versus sub f equals the square root of 2 times 3.0 meters times 12 newtons over 6.0 kilograms minus 0.15 times 9.80 meters per second squared. This gives a final speed of 1.8 meters per second. Now for part B, we ask a more complex question. What if the pulling force F is applied at an angle theta, as shown in the diagram, ANT? What angle will the final speed of the block be maximized? This is an optimization problem because two competing factors are at play. First, the work done by the applied force is now W equals F times D times cosine theta, since only the horizontal component of the force does work over the displacement. As theta increases, this work decreases. However, the normal force also changes. The vertical component of F, which is F sine theta, pulls upward, partially lifting the block. The new vertical force balance, is N plus F sine theta minus mg equals 0. This means the normal force, N, is now equal to mg minus F sine theta. A smaller normal force means a smaller friction force, F sub k. To find the angle that maximizes the final speed, we first write an expression for the final kinetic energy, K sub F. Using our energy relation, K sub F equals the work W minus the energy transformed by friction, F sub kd. Substituting the expressions from the previous slide, we get K sub F equals Fd cosine theta minus mu sub k times the quantity mg minus F sine theta, all times d. To maximize this final kinetic energy, we must use calculus. We take the derivative of K sub F with respect to theta and set the result equal to 0. When we do this, the common terms F and D divide out, leaving us with negative sine theta plus mu sub k times cosine theta equals 0. Rearranging this simple expression gives us the condition for the optimal angle. Tangent theta equals mu sub k. For our specific problem, with mu sub k equal to 0.15, theta is the inverse tangent of 0.15, which is 8.5 degrees. In example 8.6, we analyze a block spring system. For part A, we have a 1.6 kilogram block attached to a spring with a force constant, K, of 1,000 newtons per meter. The spring is compressed 2.0 centimeters, or 0.020 meters, and then released from rest. We need to find its speed as it passes the equilibrium position, x equals 0, assuming the surface is frictionless. We model this as a non-isolated system where the spring does work on the block. Our energy equation is delta K equals W sub S, where W sub S is the work done by the spring. The change in kinetic energy is 1/2 m versus final squared minus 0. The work done by the spring as it expands from x max to 0 is 1/2 kx max squared. Setting these equal, we solve for versus final and get 0.50 meters per second. Now for part B, we analyze the same situation but with friction. We add a constant friction force, F sub k, of 4.0 newtons that retards the motion. We want to find the new speed at x equals 0. We model this as a non-isolated system due to the work done by the spring, and a non-conservative system due to friction. Our full energy equation is delta K plus delta E sub int equals W sub S. The change in kinetic energy is 1/2 m versus final squared. The change in internal energy is F sub k times d, where the distance d is the compression, 0.020 meters. The work done by the spring, W sub S, is still 1/2 kx max squared. Our equation becomes 1/2 m versus final squared plus F sub kd equals 1/2 kx max squared. Solving for versus final and plugging in the values, we find the new speed is 0.39 meters per second, which is less than the frictionless case, as expected. Let us explore a what-if scenario for this example. What if the friction force were increased to 10.0 newtons? What would the block's speed be at x equals 0? We can solve this by comparing the energy input from the spring to the energy transformed by friction. First, the work done by the spring, W sub S, which is 1/2 kx max squared, calculates to 0.20 joules. This is the total energy the spring adds to the block. Next, we calculate the energy transformed by friction, delta E sub int. This is F sub k times d, which is 10.0 newtons times 0.020 meters, and this also equals 0.20 joules. The change in kinetic energy, delta K, is the work from the spring minus the energy lost to frictions. So, delta K equals 0.20 joules minus 0.20 joules, which is 0. Because the block started from rest, a change in kinetic energy of 0 means its final kinetic energy is also 0. The block arrives at x equals 0 with a final speed of 0. Let us summarize the key concepts of this section. The standard work kinetic energy theorem is not valid when kinetic friction is present. This is because the displacement of the point of application of the friction force is not calculable, so the work done by friction is also not calculable. Instead, we derived a modified energy relation for a non-deformable object. W minus F sub kd equals delta K. Here, W is the work done by all forces other than friction, F sub K is the constant friction force, and D is the path length. We also defined the increase in internal energy due to friction, delta E sub int, as being equal to F sub K times D. This shows how friction transforms kinetic energy. Finally, this allows us to state the energy model for a non-isolated system with friction. W equals delta K plus delta E sub int. To conclude, let us review with two questions. First, why can we not use the standard work kinetic energy theorem, W net equals delta K, when kinetic friction is present? What specific quantity did we determine is not calculable? Second, recall example 8.5 part B, where a block was pulled by a force at an angle. Why is the maximum final speed achieved at a small positive angle, such as 8.5 degrees, and not at an angle of 0 degrees? What two competing factors are being optimized in this situation?